Okay, this is the lecture video for MAC1114 trigonometry. We are in section 7.5 where we're going to be looking at the sum and difference formulas for sine, cosine, and tangent. We use these formulas when we are trying to evaluate angles that don't appear to be related to quantities inside of a special right triangle, but if we use the sum and difference formulas, we can relate the kind of angles that they're throwing at us in this section, like a 75-degree angle or a 105-degree angle. We can relate them to the values that are inside a special right triangle, which has been the main theme of what we've been using by way of these sum and difference formulas. Okay, so introducing first the cosine formulas. This is when you have the sum of two angles that you are evaluating through the cosine. It can be expanded in this way. So what you're going to do is be presented with an angle that you really can't evaluate in an exact form unless you split it up. It will be expanded in this way, and by the time you expand it, you will have related it to the angles inside of a special right triangle. So you can do the sum formula for cosine, or you can do the difference formula for cosine. Notice that the similarities in both of these formulas, just as a way to help you memorize the formulas. The product that you see in the front for both of these, whether it's the cosine of a sum or the cosine of a difference, is cosine, 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 cosine. So it's like a homogeneous type of formula where it's nothing but cosine, product of cosine in the front, nothing but product of cosine in the back. These products in the back are also homogeneous. They're made up of nothing but sine, nothing but sine. And the angles that you're seeing there, alpha and beta, are the two angles that you're going to split it up into. Also, you're going to have to memorize what does the sine look like on the expanded side of the equation versus what you're starting with. If you're adding two angles to create the angle you've been presented with in the problem, then you will have the opposite sign in the expansion. Notice that this one's the same way. If you have to subtract two angles to create the angle they're throwing at you, this will be the opposite sign. So you have to memorize that on the expanded side, which is the way you're going to write it before you actually get into the evaluation part, that sign will be the opposite of what you started with. However, in the sine formulas, notice that they are not homogeneous products like you see in the front where this product's made out of nothing but cosine. Here it's a mixture. So it'll be part sine, part cosine in that product at the front for both of these formulas having to do with the sum for sine or difference of angles for sines. So sine times cosine, this one's sine times cosine. And this product back here, same thing. Part sine, part cosine. What you have to notice here, though, is that even though both of these products are made up of part sine, part cosine, notice that alpha is with sine in this front product, but it's with cosine when you come to the back product. The beta is with cosine, now beta is with sine. So you need to switch those angles. If the alpha is with sine, it will then get an opportunity to be with cosine. If beta is with cosine, it will then be with sine in this back product. So the angles switch. This is the same kind of formula. Both products are part sine, part cosine, and if alpha is with sine, it will now be with cosine in the back product. Beta is with cosine, now it's with sine. Notice what's going on with the signs in the expanded version. The sign that you originally used to create the triangle that you're being asked to evaluate, if it's a plus sign that you're using in between your two angles, it'll be a plus sign in the expansion. Minus sign here, minus sign here. So in the sine formulas, you have hybrid products, part sine, part cosine, whereas in the cosine products, it's homogeneous products, cosine, cosine, sine, sine. Also, there's the thing with the signs. What you start with, you will switch. But in the sine formulas, you will not do that. It'll be same sign in the expanded sign as when you started. Okay, so let's get at the problems using these formulas and referring back to them as often as you like as we go through the problems. Okay, in example 1, they're just trying to get the definition out of you. So they're saying the sine of a sum of two angles, and you just have to look at the formula. Of course, you're going to be working towards memorizing them. And when you're doing this true-false statement to see if what they've written, I would just write it out yourself and then compare it to what they've given you. Okay, so here we go. For sine, this is the formula. Okay, those sine formulas, look at those one more time. They are hybrid pairs, a little bit of sine, a little bit of cosine in each of these products. Don't forget to switch the angles. And remember, the sign in the expansion is the same as the one inside the parentheses. Okay, so sine of alpha plus beta is equal to a little bit of sine, a little bit of cosine in that product, a mixture. I'm going to put alpha here and beta here. I'm going to keep that sign the same. I'm going to do a sine times cosine pair. Now, I know that they write the back one as cosine times sine, but you can write it the same way. You can write sine times cosine. What you do have to remember, the only important thing in this hybrid product that you're forming is to remember to switch those angles. If alpha was with sine, it will now be with cosine. And this one will switch also. So that is what the sine of two angles added together is. Now, is that what they've given you here? They gave sine of alpha, sine of beta. They're giving something else here. So is this equal to this? No, it is not. This is what the sine of alpha plus beta is equal to. Just a direct formula that they're trying to draw out of you. Here you actually get into a problem that you're going to have to simplify in order to answer true or false. So let's expand. We have the difference of two angles, and that's all about what this section covers. Sums and differences for sine, cosine, and tangent. So the cosine formulas are homogeneous products. So it goes cosine times cosine in the front, giving the angles to each of these cosines that are in the parentheses. Then for the cosine formulas, that sign that's in the parentheses, it switches on the expanded side. And then it goes another homogeneous pair in the back, all signs. Okay, so now trying to simplify so we can determine whether cosine of pi over 2 minus theta is indeed actually equal to cosine of theta. Well, we've yet to discover that. We do know that there are specific values at pi over 2 that represent the sine and the cosine, and I'll just remind you of those. When you're on the unit circle and you're at the pi over 2 location, as this indicates and this, what are the values there? Well, if you're on a unit circle where the radius is 1, whether you go this way, up, left, or down, you're at a point that has an x-coordinate of 0 and a y-coordinate of 1 unit up in the air. This always represents the cosine, the first value, and the second one represents the sine. So, cosine at pi over 2, 0 times. So now I'm just replacing this trig word at this location with the value that it is equivalent to. Sine at pi over 2 is 1. So I'm replacing this trig value at the pi over 2 location with 1. And then it's, you don't have to put that in parentheses. So 0 times anything, 0. 1 times sine, sine. So what cosine of pi over 2 minus theta is equal to, by way of these expansion formulas, is just sine. And they tried to claim that it was equal to cosine, so this was a false equation. Okay, moving to number 3. In problem number 3, says use a sum or difference formula to find exact values. Now what you want to relate these to As you break them up using either sum or differences, because these problems can be done both ways, is you want to relate them to the angles inside a special right triangle, or angles that those 30, 60, and 45 degree angles are related to. Like you may want to use an angle whose reference angle is either 30, 60, or 45. So you're either going to use the actual angles 30, 60, or 45, or something that is related to it by a reference angle that's 30, 60, or 45. So this is just easy to see that 75 is made up of 30 plus 45. That's an easy way to get 75, but then to also be able to apply the sum formulas for sine. So that sum formula for sine, now as I expand it, this is equal to, those formulas go like this: a little bit of sine, a little bit of cosine. They are hybrid pairs. Take that first angle and give it to the first trig value, get that second angle, and give it to the other one. Then those formulas continue on their expanded side to use the same sign that's in the parentheses, and then another hybrid pair. So another sine times cosine pair. But with these sine formulas for sum and difference, the angles switch. So if 30 was with sine, it is now going to be with cosine. And if 45 was with cosine in this product, this front product, now it'll get a chance to be with sine. Okay, reminding you of the values at 30. So in a 30 degree situation, that means 30 degrees is your central angle. Always across from the 30, 1/2. Across from the 60 would have to be its complementary partner. Across from the 60 is the long leg. Okay, this was the short leg, long leg scenario, hypothesis 1. Also reminding you of the 45 degree thing. I don't know that you need to draw this, but that's the one that's the easiest to remember because both legs are equal. And that's when your central angle at the origin is 45 degrees and this other angle is 45 degrees too. I'm not going to try and squeeze that in there. Okay, now pulling the values off of these pictures and plugging them in for each of these four values. Okay, first it's sine of 30 times cosine of 45. We're going to put a value in for each one of these trig words at the specific location that it mentions. So sine of 30, that means go grab the sine value off this picture. Remember, this is called y, which is the same thing as sine. This is called x, this horizontal leg, same thing as cosine. Likewise on the other triangle. So the sine off of the 30 degree central angle picture would be 1/2. And the cosine would be this square root of 3 over 2. Oh, we're supposed to be going for 45. So cosine of 45 would be this. Square root of 2 over 2. This is the sine, just like I mentioned here. Vertical leg is a sine, horizontal leg is a cosine. So this formula calls for cosine off the 45 degree picture, which is that one. And then sine off the 45 degree picture is square root of 2 over 2, and the cosine off the 30 degree picture, cosine off the 30 degree picture is square root of 3 over 2. Okay, multiplying these, top times top, you get square root of 2 over 4. Over here, you get square root of 3 times square root of 2. Since they're both the same kind of radical, you can multiply those radicans up underneath the same radical, and then get the denominators. You can leave your answer like this. You can also present it as one fraction. Like this. You can also write it like this. You can pull out the coefficient, which would be 1/4. I've seen it written like this, just telling you all the different ways that the software you're using to do your homework, how they might try to make you write it in different forms, and they all happen to be equivalent. So you can write it like that and pull out that coefficient of 1/4, make it look more like a coefficient. And they could even really drive you crazy and factor the top. Square root of 2 is part of both of these. They could actually factor that out. And then after factoring out square root of 2, they could write the top like this. Square root of 2 times what would give you that first term back? 1. Square root of 2 times what would give you this? Let me make this a little bit smaller. It's infringing on my space. Okay, so square root of 2 times 1 would give you that back. Square root of 2 times square root of 3. I've seen answers written like this as well. And they'll indicate to you, because typically they'll give it in multiple choice and then the denominator was just 4. So it can be written in any of those. 2 separate fractions, pull it together as one fraction, pull out the coefficient of 1/4. You could also factor on the top. Okay, so just keep that in mind as you write your answers. I'm just going to leave mine as 2 separate fractions because the point of these lectures is to demonstrate how to apply the formulas. But also I just wanted to give you a heads up that they can ask it in any of those forms, the final answer. Okay, so this one is cosine. Notice that both of these examples 4 and 5 are in radian form, and you're probably going to be more comfortable doing it in degree form, so you might want to quickly figure out what this is in degrees, because it'll probably be easier for you to split it up. So this would just be 5 times 180 divided by 12. You can pop that in your calculator, which is 5 times 180 divided by 12. Okay, so 75, you're right back at 75 again. And that's going to be a lot easier for you to deal with than thinking of, oh, what fractions do I split up? So, but you are welcome to leave it in fraction form if you're comfortable with that. So this will be cosine of, remember we're always trying to relate them to the angles inside a special right triangle or something that at least has a reference angle of 30, 60, or 45. So this will be we just did this in the previous problem, 30 plus 45. This one just has a different formula. So cosine of 30 plus 45, well that formula goes like this. Homogeneous pair in the front, not homogeneous product, I like to call it. Switch the sign, and then a homogeneous product in the back, all sine. This is all cosine, this is all sine. Not a mixture of sine and cosine the way the sine formulas are. Okay, we still have our pictures that we can look at from the previous problem. So cosine of 30, we need a cosine of 45. Sine of 30 is 45, whether it's cosine or sine is just square root of 2 over 2. Cosine of 30, you can look at the picture if you want. Here's the triangle with 30 degrees at the origin, central angle, and the cosine is this horizontal leg. So square root of 3 over 2. Sine of 30, well, that was the vertical leg of this triangle with the 30 degrees at the origin. And here you get square root of 3 times square root of 2, square root of 6 over 4 minus 1 times square root of 2, square root of 2 over 4. I'll pull it together as one fraction, but I'm not going to give all forms of this answer because I've already demonstrated the different ways that they can manipulate that just because they feel like asking you for it in that form. Not that they are different answers. What you see right here is the same answer as that, just in a different form. Likewise, for example 5, again, you might want to put it in degrees. It's just probably going to be easier to split up. So that would be 23 times 180 divided by 12. 180 is the same thing as pi. So this would actually be equivalent to sine. Just, get a quick version of what that is. 23 times 180 divided by 12 is 345. Okay, so this is a pretty big number, but I think, one clue about what you should split this into is just by realizing what one of the angles is, that you're going to split it into two angles, but do you see how this ends in 45 degrees? So that's going to be one of your angles, and whatever is left over after that is going to be the other one. So this is going to be, and the reason that this is a good way to split it is that I was telling you, you should split it into angles. You need to split it into angles that are either 30, 60, or 45, as the actual angle that you're seeing there, or at least use an angle that's related to 30, 60, or 30, 60, or 45 as a reference angle. See, if you spin to 300, you're going to have a 60-degree reference angle. So you're still going to be working inside of a special right triangle. So actually use the angles that are inside a special right triangle, or ones that have reference angles that are 30, 60, or 45. Okay, so now let's break this up using the formula. Formula for sine goes sine times cosine in both of the products that you're forming. So sine times cosine, using these two angles that you've split it up into. The sign that's in the parenthesis is the same one that's in the expansion, and then another sine times cosine product. Only this time switch the angles. Give the 45, not to the cosine again, this time give it to the sine, and the 300 will go to the cosine. And then you're just going to plug in values. So you either know these or draw a picture. I would suggest drawing a picture just so you get the signs right for the 45. Now, I want to keep reminding you that every time it says find an exact value, you are not to give a decimal, because you wouldn't have to know the formulas, you wouldn't have to show that you know any of the algebra, you'd literally have no work. You would just be pressing it in. So make sure you're doing it just as you're being instructed in these lecture videos. Okay, so square root of 45, we already, not square root of 45, sorry, cosine of 45 as well as sine of 45. We have that picture that we keep using. Both sine and cosine are square root of 2 over 2, so I'll go ahead and plug that in there as well as here. Here's a picture for 300. It's rotating all the way to 300. This is the 360 mark. It's 0 when you first leave it. It's 360 by the time you spin around and get right back into quadrant 4. So your spinning arm stops there, 60 degrees before you got back to 365, because you were only rotating to 300. So you had to stop 60 degrees before you got back to 360. Close this up. Form your right triangle, and there you go. That 300 is related to a 60-degree angle. This makes this the long leg. That vertical leg is always your sine value, and that would make this the 30-degree angle. Therefore, this is the short leg, and the horizontal leg of your triangle is always the cosine. Okay, hypotenuse is just 1, but you don't need that. Okay, so the sine at 300 is this negative square root of 3 over 2, and the cosine of 300 is this 1/2. Then once you have values that you've replaced each of these trig words with at their specific location mentioned, then you can just multiply top times top, bottom times bottom. So this is negative square root of 6 over 4 plus square root of 2 over 4. And you can give that as one fraction if you'd like. You can put the positive numerator first if you want to. Same answer. Okay, give this answer or that answer. And you know that there are variations of that, which I mentioned in example 3. Things that you can do to give equivalent forms of this answer. Okay, moving to example 6. In example 6, we're going to find the expression that's equivalent to this. Now this time, they're giving you the expanded version and you're going back the other way. So you have to think backwards here. What is this the formula of? The ones that have these hybrid products where it's made up of one factor that's sine and the other factor that's cosine. These would be the sine formulas that are like that. And that's just purely from memorizing the formulas. So a sine times cosine product here, a sine times cosine product here, with the angles being switched, 50 for sine, now the 50s with the cosine, and so forth. You have to remember, when I bring it back to its condensed form, what's the relationship between the sine that's here in the expansion and the one that you bring it back to? So, when you're going back the other way, I'm just copying this right now, bringing you back the other way. So this is a sine formula. And the way the sine formulas work is that this sine in the expanded side is the same one that's in the parentheses, and then you can clearly see that the angles being used are 50 and 10. Okay, and then this is equivalent to sine of 60. It just said find the expression that it's equivalent to. They didn't actually say find the exact value. So when they say find the expression, that means they just took it to this level right here. Okay, 7, same thing. They're trying to get you to go backwards from what you see here. So when you have products that are made out of strictly cosine or strictly sine, I called those homogeneous products. Those are the cosine formulas. So this would just be cosine. Okay, then we have to think about what is the relationship between this sine, in between the products, and the one that's in the parentheses. Well, for the cosine formulas, they're opposite of each other. The expanded sign and the one that's in the parentheses. The angles, use them in the order they give them. So this is 15 and 30. Now this one, the directions are slightly different. Instead of saying find the expression, that means the step right before you finish the problem. And now this one says find the exact value of the expression. That means you're going to go one step further. Beyond where I landed in this problem. So where I landed in the previous problem is that I went to the point where I put the angles together. And I'm doing that now, but in this one, since they want an exact value, you're going to go further. Okay, we've used the 45-degree triangle for several problems in this section. Both cosine and sine, those are the vertical and horizontal legs, are square root of 2 over 2. So this is the exact value that represents cosine of 45. No decimals. Okay, number 8, same type of problem. It's already expanded and you're trying to go back the other way. You can put it over here. Here it doesn't matter. I'm going to do it over here since I have more room. Okay, again, the ones that go sine times cosine, like a hybrid pair, it's a mixture of sine times cosine in the front product as well as the back. Those are the sine formulas. Okay, in the sine formulas, the sine in the expansion is the same as the sine when you go back to condensed form from the place where it began. Use the angles in the order that they give them to you. So this would be pi over 12, that's given first, and then they give 5 pi over 6. So this problem, going further with this problem, is just a matter of you getting a common denominator. That shouldn't be too hard. Just multiply this by 2 as well as this. You always have to multiply the same by the same value top and bottom. So you have 1 pi over 12 minus 10 pi over 12. Okay, then we're going to bring it together into a single angle, just like we did with the previous two problems, examples 7 and 8. Well, we brought them together. There were two angles, but then we put them together. Same thing here. There were two angles. When we went back to condensed form, we brought them together. Okay, so that's what we're doing here. So 1/12 minus 10/12 is 9/12. Okay, now I'm going to reduce that so you can recognize it. This is the sign of negative 3. 3 goes in there 3 times, 3 goes into the bottom 4 times. Okay, notice that this says find an exact value. I'm going to leave this as fractions just to give you a little bit of practice with your fractions instead of converting everything to degrees, because they are very much leaning towards you giving radian type answers. I want you to try to remember the even and odd properties here. The even and odd identities. This happens to be an odd function, considered an odd function. You don't leave the negatives in the arguments. You're going to simplify it after dealing with this. It either goes away because it's an even function, or it comes out and becomes the coefficient. So we can rewrite this as sine of 3 pi over 4. So what we want to know is, hey, what is the sine value at 3 pi over 4? And then we can put a negative in front of it. So here is a picture of a 3/4 pi rotation. This is 1 pi over here. We know that location as 1 pi. That is equivalent to 4/4. 4/4 is 1 pi. So if you're going to rotate to 3/4, okay, we rotated to 3/4, which means that the reference angle is 1/4. Okay, that's your reference angle. Very, very much important. That 1/4 pi is the same thing as 45 degrees. 180 divided by 4 is 45 degrees. So this leg, which is considered the sine, your vertical leg is always considered the sine, or you can also call it the y-coordinate. This horizontal leg is the same. You can call it x, but it represents the cosine. So when we come to finish this problem, they're wanting the sine at 3/4, which is just the leg that is considered the sine after rotating to 3/4 and figuring out what the reference angle is to build the values on your legs. So this represents the sine. We come in here and we put square root of 2 over 2, and we bring that negative down right in front of it. Okay, and that is the final answer. Okay, moving on to number 9. In problem number 9, it says establish the identity. So when you're establishing the identity, you're going to use the formulas for sum of a sine, the sum of two angles for sine. So that would be, I'm going to do some of the work up here. The sine formulas go like this: a little bit of sine, a little bit of cosine, and then you use these two angles. So pi over 2, this other one's theta. Then whatever's in the parentheses, the same thing as in the expansion. So we're trying to establish by using the formulas and expanding this using the formulas, is it really equal to cosine? It either is or it isn't. So we have this so far, a little bit of sine, a little bit of cosine, then we have another product just like that. And they may decide to write this back product as cosine and then sine, but you must remember to switch the angles in this formula. So now the theta comes to the sine, and the pi over 2 now goes with the cosine. And then they gave us cosine of theta on the other side. Okay, so now they've gone further. They have expanded it like this, and then they've shown what each of these is equal to. So let's not jump to the answer on the right-hand side. Looking at these answers, I see that they did the expansion, and then they also plugged in values where values could be plugged in. For instance, there is a value at pi over 2 for sine, because they're actually telling you where to rotate. So once you know where to rotate, you can come up with numbers that represent or replace these two terms right here. So sine of pi over 2, once again, here is pi over 2. You're inside a unit circle with radius of 1. So the x-coordinate right at pi over 2 is 0, and the y-coordinate is 1. This represents the sine. This represents cosine. So if you want to come in here and start plugging in, sine of pi over 2 is 1 times cosine theta plus sine of theta times cosine of pi over 2, which is 0. And they're saying, and then this is what they gave us on the right side of the equation. Okay, so I took all of this, sine of pi over 2 plus theta. I expanded it using the formulas that are presented in this section. The sine formulas for summation are sine times cosine for the front product, sine times cosine for the back product, using the angles here but switching the angles in the back product. I then went to pi over 2 and went and grabbed the sine value, which was 1 times cosine theta. At that same location, pi over 2, I grabbed the cosine value, which was 0. This is going to go away, leaving you with just cosine of theta, which is why this expansion leaves just cosine, and they're claiming that it's equal to cosine on the right-hand side, which in fact it is. So let's just pick out the answer that mimics the steps that we've just gone through. Okay, so it was, should have been, this is wrong, because this goes sine times sine. That's not the formula for sine of the sum of two angles. This one goes sine times cosine, so let's look for any mistakes. It goes sine of pi over 2 times cosine of theta minus cosine of pi over 2 times sine of theta. So that's all right up to that point. And then they went in and plugged in a 1 for sine at pi over 2 times cosine of theta. It's right up to that part. And then they did 0, just like we had, times sine of theta. And that was equal to, so everything there is correct, and this is the correct answer. Nothing wrong with that one. Okay, then we come to the sum and difference formulas for the tangent function. So this new formula, and this will be our last formula in this section, says the tan for the sum of two angles is expanded in this manner. Both of these are fractional expansions, so these are going to be the most work out of all the problems. And you're doing, when you expand it and create these fractions, the top of the fraction will be as though you expanded the tan word into both of these angles. So it'll be tan of alpha plus tan of beta. That'll be your numerator, just like this one on the top is the same thing. Just distribute that tan into both of those angles. Tan of alpha minus tan of beta. That's the top. That's how you get the top. Then the bottom of both of these fractions have a 1 in the lower left-hand corner. This angle is the opposite, this sign is the opposite of that. Same thing here. Whatever sign you have in the top, you got the opposite there. And then it finishes in the lower right-hand corner in the denominator with a product of these two terms, tan of alpha times tan of beta. And you see that here as well as here. Okay, I am going to complete problem number 10, and then I'm going to do numbers 11 through the end of this particular section in the second video. Okay, so example 10, they're just trying to elicit the formula out of you. Which one of these is the formula for tan of alpha plus beta? It would be tan of alpha plus tan of beta on the top, so it can't be that one. Can't be this one. This one, tan of alpha plus tan of beta. Then there should be a 1 in the lower left-hand corner in the denominator. And then finishing off with a product, but these two signs should be opposite, so that doesn't work. So it has to be this one right here. Tan of alpha plus tan of beta. 1 in the lower left-hand corner. Signs are opposite. Product in the, as the second term for in the denominator. So that is the answer for that. Okay, I will be doing numbers, examples 11 through 14 in the second video.